name is Julio Meza, and I'm really excited and a little nervous to present to you guys my research that I did this summer under the mentorship and guidance of Rosa McGuire at Tad Bukami's lab at Stanford University, where we investigated the impact of heat waves on nectar microbes in sticky monkey flower. If you're unfamiliar with sticky monkey flower or Diplacus aurantiacus, here we have a really lovely photo of a young flower just a couple of days open. It's very young, and I actually encourage you guys to go to a local trail yourself and see them for yourself. They bloom from early spring, so about early March to June, and you'll very easily be able to see them. A really cool quality about the floral nectar is that when the flower initially opens, it's sterile. And this is really significant to microbiologists like my mentor and maybe myself in the future, for the fact that it provides a really simple and straightforward system to study nectar microbes because they're in an isolated environment. Here we have a photo of a hummingbird now feeding on a sticky monkey flower nectar. But what people won't tell you on the trail or in your lab class is that a hummingbird is never just feeding on floral nectar. It's actually introducing microbe species to it. The two most commonly found microbe species that you'll find in floral nectar is a yeast species known as Mejnicophia ricopii and a bacterial species known as Acinetobacter nectaris. And what's really cool about this is that we already know that the order of arrival in this, or their history order, matters. It has subsequent effects on their community assembly. And this is really what we wanted to focus on, their interactions with one another and how they're impacting each other. One other factor that we want to look at is temperature and how they're impacting the interactions amongst these two, especially when it comes to something like climate change. Since climate change affects life at all scales, it affects us, right? So I think this is a really interesting system to look into, and also just have a better understanding the dynamics between these two microbes and how they are then changing nectar composition and subsequent visitation by the hummingbird, which then will affect pollination and seed set production. So how did we do that? We mimicked the system in the lab, and I got a little carried away, but how did we do that? We did that by applying 3 different temperature regimes. And the first one you'll see is a pretty peach color at the top. It's a no heat wave regime. It was a controlled, but it had a fluctuating daily temperature between 12 and 24 degrees Celsius. Next, we had an orange for week 2. The color is orange, and this is signifying our low intensity heat wave, which lasted for 2 24-hour cycles. And the range went from 12 to now 30 degrees Celsius, which is very hot. Next, week 3, we then observed the interactions of the nectar microbes in the floral nectar when we hit them up to 36 degrees Celsius, still with the 12 Celsius baseline. Okay, and the way that we're able to mimic these flowers inside the lab, because, well, it's really difficult to just manage them all, is we use what we call artificial flowers, and we use PCR tubes to make them. So these PCR tubes are acting as our artificial flowers, and we then fill them with artificial nectar, which has very similar properties to nectar found in the wild. And we then inoculated or mimicked an Anna's hummingbird coming to feed and introduce microbes into the artificial flower. And we paid close attention to the order of arrival. So we wanted to see how they were being affected depending on these 3 different treatments, which correspond to their arrival order. Here you'll see at day 0 that when we introduce the yeast first, and then we introduce another treatment where bacteria is introduced first, and then where we introduce the 2 species together. The following day, we then introduce the other respective species. So if we inoculated our artificial flowers with yeast on day 0, we then inoculated it with the bacteria species and vice versa. Here was my daily protocol. Every day in the lab, here's just like a photo of all our PCR tubes, our artificial flowers in our ecotherm, which we programmed to mimic these daily fluctuations and heat waves. And we quantified 2 things primarily, or I quantified 2 things primarily this summer, which is nectar pH and estimated microbial abundance, or CFUs, which just tells you how many are inside the nectar. at any given moment. And we just use pH strips. And the way that we were able to estimate this was by diluting our nectar and spot plating them onto species-specific nutrient-rich agar. If you have questions about how they're species-specific, feel free to ask later. Here we have some really good data. More pretty colors. They correspond to the same temperature regimes that we talked about earlier. But now I want to highlight here on these two panels where you see at the top, we have arrival order. The bacteria first, when they are introduced and when the two species are introduced together, you see a dramatic shift in the pH where they're dropping from 5.5 to 2.5 in one day. So this is one dramatic and insanely quick. You're not seeing the same shift in the yeast species introduced first. There is a change in pH, but not as dramatic or as intense in time. Here we have the daily microbial abundance, or the CFU counts. Pay close attention to this y-axis. It is now in logarithmic scale because microbes grow very quickly and there are a lot of them. And the bottom is still time in days. Also pay close attention to these lines. They now mean something. The defined lines are going to mean yeast species, and the dash is going to correspond to our bacterial species. Here you'll see in our first one something really interesting that I mentioned earlier. Well, not interesting, but it's really highlighted here in the second panel, where we see bacteria introduced first. You see that there are very strong priority effects happening, which is what I was mentioning earlier, where if something arrives first, it's going to have effects on the community assembly afterwards. So you're seeing here that bacteria arrives first is taking advantage of whatever nutrients are inside the floral nectar and just growing at this crazy rapid rate and then just continuing to do so. And the same thing is not happening to the yeast. So they're actually growing really slowly, which tells us that something very likely changed inside the nectar composition so that it's not favorable for growth, which is telling us that they just have antagonistic effects on each other. And then here in this yeast species, there's a lot going on, but we want to highlight here in this dashed line for the bacterial low intensity heat wave that at day 3, the bacteria are starting to die off, but you don't really see that on the other two panels.
Yeah.
Okay, cool. Okay, so here are our next steps. We would obviously want to do this for longer than a week, over a 3-week period, maybe over multiple flowering seasons. We also want to do some nectar chemistry analysis. We have them stored and frozen in the lab. And we also want to see the relationship between nectar community composition on plant fitness or seed set production, right? And once again, if we can understand how this system works on a small scale for like hummingbirds and sticky monkey flower, then maybe we can relate and apply this. Maybe we can relate this to other patterns in ecology and recognize them and apply them and maybe it may have implications for biodiversity, agriculture, many things. Feel free to ask questions. Okay, thank you guys. Thank you.